طيب بسم الله الرحمن الرحيم. We talked about wireless sensor networks, and we have mentioned the fact that one of the biggest challenges for wireless sensor networks is the limited energy, and because the nodes are battery operated, we need to manage the power and the energy of the battery carefully, in which case we need to optimize the idle times. We need to minimize the listening times when we have to listen on the channel. And we have mentioned the ultimate challenge that we have is that ideally what we would want to do is we want to be in a sleep mode all the time, except if there is a signal which is coming to the receiving node. So the node needs to be in a sleep mode and needs to be triggered to get to the wake up mode only when there is a signal sent to it. But if the node is in a sleep mode, it cannot actually decode the signal. So this is a conflicting thing. So in order to be able to decode the signal, to know whether the signal is coming to us or not, we need to be in an awake mode. So the only way is that we need to have some guessing or some estimates about when should we be in a wake-up period, when should we be in a sleep period, and this decision is based on heuristics in general. And based on this heuristic, the throughput and the energy consumption and the latency in terms of reception and transmission, they all get affected. Okay, based on how much time we are in a wake-up period. Well, if we are in a wake-up period all the time, then there is no latency. Whoever is trying to send to us will be able to receive. However, the power consumption will be very high because we keep listening on the channel for no reason. If the active period or the wake-up period is too short, then we, in a way, enforce the sender that the sender has to wait for us until we are in a wake-up state. Or if the sender tries to send and we are in a sleep state, we will miss it, right? So these are all challenges and problems that arise in sensor networks that we didn't otherwise have to deal with in the case of wireless mesh networks or in any other networking paradigm. So the challenges or the requirements for the wireless sensor networks is that we know that the transmissions are very costly because the transceiver needs to spend very high power to be able to transmit, and depending on the distance between the transmitter and the receiver, this power can be high, and in which case we have to spend too much energy. Receiving is also almost as expensive, maybe a little bit less, and we explained that from the hardware perspective of the transceiver. However, I don't really have much control in transmission and receiving because these are active functions that the sensor must do or the sensor has to do, right? If the sensor has data to send, it has to send. So I would call this a cost that we have to pay. What we really don't have to pay, at least 100%, is the idle period. During the idle period, I don't have any anticipation when the signal is going to come, yet I have to keep listening on the channel. I have to keep sensing the channel. In many cases, for no reason. And even though this is a little bit cheaper than transmission and receiving, however, the idle period maybe is the most frequent function that the sensor usually has to do, right? In order to be able to receive the data correctly. The other thing is that some problems that arise when we talk about energy conservation in wireless sensor networks, for collision-based protocols, we know that collisions, they cause both signals to be unusable, right? In which case we have to retransmit. Remember, collision is different from packet loss. For packet loss, we lose the packet because the channel is bad, right? But collision, even though the channel is good, but two nodes are trying to send at the same time, in which case collision will happen. And when the collision happens, unfortunately, we have lost the energy on both sides, right? Both the nodes that are trying to send at the same time and they collide, they actually waste this energy, which is really a motivation for us that we should try to reduce and hopefully eliminate collision altogether if we can. But we know that the only way for us to eliminate collision completely is by having the schedule-based protocol. Schedule-based protocol means that you need to divide the resources of the channel uniquely so that in one point of time or in one range of frequency, only one node can send. This is the only way for us to eliminate collision altogether. And the problem with that is that you have to allocate these resources based on, again, some estimate. And you're not sure whether this estimate is 100% accurate or not. So,
ideal is still expensive because of listening?
Right, because idle is still, well, if you are in idle mode, but you're not in sleep mode, then you are still consuming power even though nobody's trying to send you anything or you are
listening
not
for receiving.
Yeah, listening because you don't know whether someone is sending you anything or not. But idle here, during the idle mode, what you normally do is that you have to sense continuously the channel, whether there is someone trying to send any signal. If someone is trying to send any signal, then you decode that signal to know to read the physical address to know whether this signal has data for you or not. Right? That's what you need to do. But in idle period is different from sleep. Of course, during the idle period, all the circuits are powered up. So you are consuming energy anyway. So the hardware circuit is consuming some energy even if you're not sensing the channel. Because all the circuits are powered up. Okay? So you would want to turn off the circuit and go in a sleep mode. As we said before, when you are in a sleep mode, then depending on the sleep level, sometimes the only thing that can wake you up is hardware interrupt. Or you can wake up by software interrupt using timer. Okay, so these are different sleeping levels. So overhearing here is what we call the idle period. The overhearing here talks about the fact that we know that there is a signal coming, and then we read the signal, which means we decode the signal, and then we figure out that the physical address in that frame is not my physical address. So I'm overhearing, okay? I'm overhearing something that's not for me. And the only way for me to know that it's not for me is the fact that I have to decode the signal and convert it into digital and read the physical address, and then and only then figure out that this is not for me. So we need to minimize the overhearing. We need to minimize the fact. So in other words, we need to have some accurate prediction that at this point in time, someone will try to send me useful data. If I know this accurately, then I can sleep, I can go to sleep and like adjust the alarm clock to wake me up a little bit before the data comes. Okay, but this future predictions are usually not very accurate, and it has to be done through some heuristics, which means that there is some possibility of inaccurate wake-up periods. So idle listening here talks about the fact that it's like overhearing. So sitting idle, and I'm not hearing anything, but I'm idle. Okay, idle, which means that I'm just listening to the channel and there is nothing coming, no signal. So idle is a little bit different from overhearing in the sense that idle is there's no analog signal coming from the physical layer point of view. Overhearing talks about the fact that there may be some signals coming, but when I try to decode the signal, I find that the data inside this signal is not for me. Right? So that's the difference. In addition to that, there is some protocol overhead. Of course, any protocol has some overhead, which increases the size of the frame by adding some headers, and in some cases, some trailers as well. And this header and trailer, it consumes also some energy from the physical layer point of view, because the actual data that you send, or in other words, the bandwidth or the throughput is much more than the good put. The good put is the amount of data the amount of useful data from the application point of view. But the throughput talks about the fact that this useful data, in order to send it, I have to add some protocol overhead. Okay, and then make sure that the data with the protocol overhead, they have to arrive on the other side. That's what we call throughput. Okay, so this protocol overhead spends also some energy. In addition to that, of course, because the protocol sometimes is very complicated, which means that you need to have like beacons, you need to have RTS, CTS, and you have to go back and forth many times, right? So the more complex the protocol is, the more energy you have to consume. So it would be nice to have low complexity solution. Okay, but all these are conflicting requirements or conflicting objectives. You cannot meet all of them. You have to address one or two of these at the cost of the other factors. And it's our responsibility as engineers and as designers or developers to create some kind of a compromise between all these factors. This is the key. This is the key issue here. So we need to address these challenges, whether individually or collectively, and create some kind of a compromise. So based on that, we design a set of protocols for the wireless medium access control. And this taxonomy we talked about before, when we talked about wireless mesh networks, it's the same categorization for MAC techniques. There is centralized. For centralized, as we said before, you have someone to moderate the meeting. Okay, and that's usually less challenging in the sense that if you have one moderator or one controller, it's usually easier to control when to access the medium. That doesn't mean that you will eliminate collision altogether, but in some cases you can. So schedule-based, when you have centralized scheme, is usually very easy. Contention-based happens even in the centralized case, when you have some like hidden terminal problem, or you cannot control things to the maximum. So even if we are in a meeting and there is one moderator, someone might violate that and talk and have some side discussion, in which case the collision will still happen. In the distributed case, it's usually much more challenging, because in the distributed case there is no single controller, which is good because there is no single point of control usually means a single point of failure as well. If this controller is absent or not functioning, then everything is down. So always, this is a rule. Single point of control meaning single point of failure. Okay? So distributed in that case is useful in the sense that it does not have this single point of failure, and it's much easier to have some freedom for the nodes or some people in the meeting to talk whenever they want, which is kind of nice. But the problem here is that the contention happens a lot, with a lot more frequency and a lot more strength compared to the centralized case. So can we have some schedule based in the distributed case? Yes, we can. So we can, in the distributed case, we can reorganize ourselves. Like we are in a meeting, in a big meeting. We can reorganize ourselves, assuming that we are mature people, and create some kind of domains or smaller domains, and nominate one of us to be not centralized controller. It's not a single point of failure in that case, but a cluster head. That's what we mean by cluster head. So we divide ourselves into groups and have someone nominated between us to act as this controller. When this guy acts as a controller, he controls our group only, not everything. Okay? So this is an intermediate case between the centralized and the total distributed. So in that case, this cluster head, and we'll talk about that, this cluster head can organize and can have some schedule between these nodes, and divide the channel resources according to different disciplines that we will talk about. When I divide the channel resources, I can have a fixed assignment, which means I can have predefined time slots for nodes to send on, or predefined frequency ranges, and fix this. Or I can schedule this on demand based on the requirements of each node. So we'll talk about each one of these. So any question in this case? So this is like a categorization of. So this categorization applies to all MAC techniques, not necessarily to wireless sensor networks. But the problem for wireless sensor networks is that if we want to minimize the energy consumption, then we have to maximize the sleep time. And that affects all the traditional techniques for medium access control. It affects it badly, and we'll see how.
Regarding the schedule, it's like round robin.
Yes, yeah, round robin is some kind of a schedule-based technique. Any kind of...
there is no difference in both algorithm and centralized and distributed?
No, if you have fixed assignment, then you don't need a centralized controller. Why do you need a centralized controller? If it's fixed. Like we are in a meeting and...
we need synchronization between nodes.
The synchronization is another issue. We don't need a controller for channel access. For channel access, we don't need a controller. For synchronization, well, even synchronization can be done in a distributed way. Synchronization is a separate issue. So we can talk about it separately. Okay? So synchronization can be attained using distributed techniques, not necessarily centralized. If the assignment is fixed, then we don't need a centralized controller.
Yeah, because
it's easy.
In both design, centralized and centralized,
And
there is scheduling.
Right.
In both, they might use both algorithms maybe in
Right, yes, yeah. But sometimes round robin can be done using some kind of a pulling technique. Okay, so I pull a certain node to say that, okay, you can send now. It's like I'm in a meeting, and then I have the full control of who can talk when. So I can give you the mic, in which case I give you the access to the channel, right? And then I can give Ala the mic after you, and then go back to you. Okay, which means I'm giving you more opportunities to access the channel. I'm controlling everything. I have the full control. So in that case, it's not round robin, right? I'm giving you some higher priority compared to others. I have full control. I have the complete freedom in that case. So having said that, the approaches for designing the MAC techniques for sensor networks have gone through some levels of evolution. So many people have looked at the current MAC technique that's used as part of 802.11, for example. So we want, is there any way for 802.11 to be used for sensors? Well, let's see. In order for us to use 802.11 for sensors, well, we need some kind of power management or power optimization. We know that there is a mode in 802.11 that we can control the transmission power. That's good, but it's not enough for us for wireless sensor networks. 802, the way 802.11 works is that, as we some of us know, we have the access point, and we have some nodes. Okay. We have two modes of operation. One is called distributed coordination function, right? For distributed coordination function, even though we have the access point, but the access point does not act as a single controller to access the medium. And we resort to using distributed coordination or distributed access to the channel, in which case we use what we call a Cmpe Ca. So for Cmpe Ca, as part of the distributed coordination function, each node independently can sense the channel. Okay? If the channel is idle, which means that this node senses the channel for a specific duration of time, called sensing time. If the outcome here that the channel is empty, then I'm allowed to send right away. Okay, so you can send data right away. If there is a collision, then at this time use what we call back off. During this back off time, what we do is that we calculate a random number, okay, within a specific window called the contention window. Okay, and then we calculate, based on this random number, we calculate the time that we have to wait before we start accessing the channel again. So it's clear in that case that each node can send independently from the access point. So the access point does not work as a single controller in that case. Access point is merely just to connect us to the infrastructure from the network layer point of view. But from the MAC layer point of view, it's not acting as a centralized controller, even though it's there. Okay. So this back off uses 3 different parameters. One is the time slot, The other one is the contention window. And there is another parameter, third parameter called persistent factor. Okay? So that the time is the slot time that you wait an increment of that slot time. You can wait 1t, 2t, 4t, 8t, 7t, whatever. Okay? So the number of this time slot is calculated by generating a random number within the contention window. So you have a certain window, and then you calculate a random number within this range. If this random number, let's say 7, this means that I will wait for 70. If this random number is 3, then I will wait for 3t. So why am I saying this introduction? Because simply, well, some people might say that, okay, so we'll leave the protocol as is, which is good, because then we're not changing the protocol at all. We don't need to change our devices. We don't need to change the hardware. We don't need to change anything. We'll just fine-tune these parameters, okay, to make the 802.11 more energy aware, or more optimized in terms of energy. Well, how do we do that? Well, we can, if we increase T, then this means that we don't have to, we will wait for longer time. We will wait for longer time, meaning that we can be in a non-functioning mode, or maybe even in a sleep mode, for a longer time before we have to sense the channel again. So this way we can increase the time before which we have to resense the channel again, or we have to try to send again. So this way we save energy. Well, but we save energy with the cost of what? Of latency, right? So we save energy, but we have to delay ourselves. Okay? So that's one parameter we can control. The other parameter is contention window. Contention window is designed based on exponential backoff, which means that during the first trial of accessing the channel, each node will create a contention window of 1 or 2. Okay? So if you have a collision, then you generate a random number between 1 and 2. Which means that if you have 2 nodes contending, hopefully one will select 1 and the other one will select 2. If they try to send again at the same time, unfortunately both of them selected 1, they will collide again. So each of them will wait for time t, in which case they will wait, and then they will try to send at the same time. Collision will happen again. In that case, the collision window or the contention window will be 4, will be double. So each time you double the contention window. So the window is 1, 2, 3, 4. And both nodes will independently generate a random number within this window. If they collide again, or maybe I collide with another node, then the contention window will become 8. Okay? So I can, here in the, if I want to be like more power aware, I can increase this contention window or decrease it. Okay, in that case, even more than exponentially, in order to control the time or delay myself a little bit, in which case I don't have to sense frequently. Well, the idea here is that sensing is expensive in terms of energy consumption. So I want to minimize sensing. Okay, and at the same time, when I wait for a longer period and increase the range of the contention window, what does that mean? This means I'm reducing the possibility for collision. Because if the contention window is short, then there is a possibility that both of us will generate the same random number, and in which case we will collide again. If we increase the contention window, then this possibility, it's actually the probability that you and I will generate the same random number. Right? So the more range we use for the contention window, the less the probability is going to be. So this way, we are reducing collision. But again, at the cost of a latency. When we increase the contention window, then we might generate a random number that will allow us to wait for a very long time. In which case we reduce the collision, but we introduce latency. Right? We don't have to talk about persistent factor.
But how can collision happen if the nodes do not transmit unless they make the sensing?
Unless
they sense the channel before transmitting. So the first node here is sensing the channel.
Right.
Yeah. And then we'll know, so because no one is transmitting, so it will transmit.
Yes.
But in the middle, someone is transmitting. But why it didn't make the sensing of the channel so it can see?
That's a good question. Okay. So the thing is, if you have any shared medium, like this is a shared medium. Let's see, this is like a shared medium. And multiple nodes are trying to access that shared medium. This shared medium could be even wired, like hub, or wireless, or anything. This is a logical topology now. Okay. This is how this part here talks about the distances between these nodes together. And this talks about the time. So this is distance, and this is the time. Okay? When this node tries to send, okay, the signal itself travels through the shared line but it has to consume some time. Right?
Yes.
So, did you get it? So, throughout this time, the node that tries to listen to the channel, it may or may not know that this signal exists unless they sense for a specific time. Yani, for example, this node, maybe it senses for a time like this.
So the sensing time is to be optimized to be more or less the maximum.
Right. So even يعني this node now tries to sense for a specific time, and then here it takes the decision that the channel is empty, so it will send. Right?
Yes.
And the collision will happen here. Right? Let alone that they can actually sense at the same time and take the decision at the same time that the channel is empty. But here, this scenario talks about the fact that even if we're not sensing at the same time, also collision may happen. Okay? Because of the propagation delay. Okay? So the only way for us to eliminate collision is by having the schedule base, or by having like some sort of control, or having single moderator to moderate the meeting. So the first choice that we talked about in that uses it, which is good because it does not change the protocol at all, with the only exception of controlling the contention parameters. The contention parameters that we have are the random delay, or the random back-off time, the contention window, or the persistent factor, which we didn't talk about, and the number of retries. The number of retries talks about the fact that this is the number based on which we keep increasing the contention window more and more. So when we allow more retries, this means that we allow the contention window to increase more and more and more. Okay, if this number of retries is less, then the contention window will not increase that much. In other words, just by fine-tuning these parameters, we can introduce some energy saving, but at the cost of latency or delay. Okay, so we can, through just changing these parameters or controlling these parameters, we can have some compromise. Remember that latency and delay is not that big of a deal for wireless sensor networks. Why? Because simply the data rate requirements for wireless sensor network is not that high, right? For many applications, it's not that high. Usually, a sensor would be required to send, مثلا, temperature or pressure or something like this. It's not, so the data rates are not expected to be that high. So we can play around with these parameters in such a way that gives us the data rate that we need by introducing the latency, but reduce the sensing time and reduce the contention, or reduce the collision, because collision is very expensive in terms of energy consumption. Okay. Otherwise, if you don't change these parameters, then the normal mode for 802.11 is very aggressively contending on the channel. This is the approach. 802.11 advocates the fact that nodes aggressively contend on the channel. It's like, roundabouts. So we will try to access the roundabout whenever possible. Okay, and if there is any collision, we'll handle it later. Well, this is good if we don't care about power consumption. But it turns out that collision is very expensive in terms of power consumption, and that's why it's not good for wireless sensor networks. And because of the fact that wireless sensor network is not data intensive, it would be nice to reduce the collision by introducing some latency, which is fine, but this will help us reduce the power consumption, which is more key for the case of wireless sensor networks. Okay, so this is one simple, just fine-tuning of the parameters. We didn't do anything special. We didn't have to introduce anything new at all, which is good. Okay. The other approach is by which has been proposed in one of the research papers, is to use what we call ad hoc traffic indicator map. So what this is that we can use, so let's forget for a second about the word ad hoc. So let's consider traffic indicator map. This actually is talks about the fact that we can give information to the nodes about our intention in the future that I want to send you. Okay, so what happens here is that we can use the one controller in the system to send beacons. These beacons will tell them these beacons are sent by, of course, potentially the access point. Okay. Listen, I have a terrible handwriting. This is not it's not good. Okay, so the access point will send some beacons. Okay, and these beacons will have very useful information for all the nodes. So these beacons are sent periodically. And the good thing here is that if you have access point and we send these beacons periodically, we have centralized controller that we can use both for synchronization, which is the issue that Ala just mentioned, and for controlling this period, okay, which gives some indication to the nodes what will happen during this period. So what will happen is that this beacon will have very useful information. I will give you some duration that during this duration I have some data for you. I will give you what we call traffic indicator map. During this period, I'm sending you my intentions as an access point, my intention that I need to send you some data in the future. So this traffic indicator map will give you some future time that you need to be awake during this time. Okay? So this traffic indicator map is very important, and it happens after the beacon, right after the beacon time. So the beacon will give me the information about the whole structure, about the duration of the TIM, and the duration of the active period after that, and the duration of the entire period. So during the TIM period, each node has to be awake to receive this TIM. This TIM will let the nodes know whether the access point has data for them or not. And this is useful for downlink. So for this direction. So downlink from the access point to the nodes. If the access point has some data for these nodes, it kind of announces this during the traffic indicator map. This traffic indicator map tells these nodes when do they expect their data. In which case, each node will know or will estimate its own active period here. So this is an active period for a specific node based on knowing the traffic indicator map. Traffic indicator map gives you the future plan. This is my future plan. I need to send this node data. I need to send this node data at certain points in time. Okay? Other than this, the nodes will be in a sleep mode. So this is a clear modification of the protocol. Well, we're still using 802.11, and here we use the point coordination function, not the distributed coordination function. If you have studied 802.11 before, it works based on two modes. This is the DCF and PCF. For DCF, you have complete distributed coordination function based on Sigma CA. For point coordination function, we resort to using the access point to pull the nodes according to a specific sequence to eliminate collision altogether. So the access point in that case acts as a controller for the median, and it pulls the nodes to tell this node that I need to send you data at this point. I need to send you data at this point. And it pulls like using round robin or based on certain sequence, whatever. Okay? So this is what we call point coordination function. So during the point coordination function, there's no collision in that case. Well, traffic indicator map is a modification for the point coordination function to give you not only the pulling, but to give you the future intention. I need to give you the future intention that in the near future I will send you data or not. Why? Because if you know this intention, then you can sleep before it and wake up right before you expect to receive the the data, and then sleep after. Okay? So this traffic indicator map will help the nodes schedule their wake up and their sleep time. Okay? So this is the traffic indicator map. Well, can we move this to distributed? Yes, this is what we call a ad hoc traffic indicator map. For traffic indicator map, what happens is that in ad hoc way, there is now a big challenge, because for distributed case, who will send the beacon? Okay, there's no single controller in that case.
It has to be all the local nodes, the local controllers.
Yeah, but again, who will send the beacon?
They will select, for example, any node as a manager. It will be distributed.
Right, but
yes,
but
they will select any node.
but yeah, this is clustered. But yeah, what happens in that case is that we will create some ad hoc clusters based on each node will try to contend on the channel using Cmpe to first of all send the beacon. Whoever will listen to a beacon, it will know that, okay, this guy, I need to synchronize to this guy. I need to synchronize myself based on the beacon that I have received, which implicitly means that I have nominated this guy to be the cluster head. And in that case, I will synchronize myself to it. And then from then, we start sending the TIM and do the rest of the things. But it will happen naturally that in ad hoc, we will in ad hoc form some groups between us based on sending these beacons. So each node will send independently these beacons, and once a node listens to it, once a node listens to this beacon, it will synchronize itself to it, which potentially means that we are creating subgroups between us. Well, we have to do this in the ad hoc case. We have to do this because in the ad hoc case, we don't have a node that has access to everyone. Okay? And we potentially have multi-hop, in which case we have to cluster ourselves according to these beacons. Okay?
Nodes can receive multiple beacons, something like this.
Yes, nodes can receive multiple beacons. Well, beacons are sent in a contention-based fashion. Okay? So in that case, a node has to decide whether to put itself in one cluster or it puts itself in two clusters. What does that mean if a node is part of two clusters? Well, if a node is part of two clusters, then it has to wake up here and here. So it has to adjust its wake-up period and sleep period based on the two clusters. Or it decides that it's part of one cluster, which means that it can never receive anything from the other cluster. In which case, you are forming your topology and your links based on your decision. If you want to form more links, which means that you are part of more than one cluster, which potentially means you have to consume more energy because now you are part of two clusters. You want to send and receive nodes from multiple clusters, which means that you form more links. But this will add some energy overhead on your shoulder. So you have to spend more energy to wake up wake up based on this beacon and this beacon. Because each beacon will tell you what is the TIM period and what is the full period between receiving these beacons. So you can synchronize yourself to two beacons or three beacons if you want. Okay? Or you can decide only one, which means that you ignore the other one. Okay? It's fairly complicated, but this is the only way you can save energy. This is a clear modification of the normal 802.11 mode, but this is still in a way compatible with the 802.11 mode using the normal SISMA CA and so on, or point coordination function. So it uses either DSEF or PCF. Okay, so that's in other words, this is for 802.11. In other words, any kind of contention-based protocol can use this concept, which has been first defined by a protocol called SMAC. SMAC, or Sensor MAC, tries to create some synchronization between the nodes that are otherwise asynchronous. So the idea here is that the only way for us to optimize our sleep periods is that if we have some synchronization between us, because if we have some synchronization between us, I know when to sleep and when to wake up. So we need at least partial synchronization between the nodes, or at least group of nodes. Okay? So the TIM or ATIM use that for 802.11, but SMAC generalizes this. SMAC is just a generalized concept which can be on 802.11 or any other protocol for that matter. And the idea here is that we have wake-up periods, okay, based on which we send some periodic beacons. This beacon will tell you what is the period of that you have to be active, or you need to be active. Okay? And what is the full period, which means that all this other time, this time, you are in a sleep mode, except if you are part of multiple clusters. Okay? So if two nodes are synchronized between the wake-up period and the active period, then they can synchronize the sleep time and they can be asleep most of the time. The ratio between, so this is called active period, and this is called wake-up period. So the active period, or the active period duration, divided by the wake-up period duration is what we call a duty cycle. So the duty cycle is the ratio between the active period and the wake-up period. If the duty cycle is too low, this means that I will be active for a very short time. Okay? And I will be asleep most of the time, which is good on the energy side, but it's bad on the latency side. Right? So the wake-up period is too long, and the active period is short. So this is good from the energy conservation point of view, but it's bad from the latency point of view. Okay? If the duty cycle is 1, this means I'm not sleeping. Right? This is the other extreme. This means I'm not sleeping at all. This means that we go back to the normal contention-based protocol. We don't sleep. We don't do any energy conservation at all. ماشي? So SMAC talks about the fact that this beacon can be synchronized in ad hoc mode or in a centralized mode, right? In ad hoc mode, we potentially create some natural clusters or subgroups between us based on who will receive the beacons. And the beacons, you might have some collision for the beacons themselves. Because if we are in a distributed environment, we can send beacons, and beacons, they can collide, right? So once you start up, you listen to all the beacons around you, and you also have to send some beacons, okay? And then you have to decide. I want to be part of this group. I want to be part of this group and this group and this group, okay? Or I did not receive any beacons, and I have to wait for others to be part of my group, which means that I'm the synchronization node in that case. Okay. Once we synchronize ourselves together, then this active period is a fixed. So the beacon will tell you what is the active period and what is the other period which you have to be asleep, or you can be in a complete sleep mode, because you know the active period and you know the total period, which means that you know the duty cycle, in which case you can be in a sleep mode otherwise. Okay. This assumes that during the active mode, during the active period, I'm expecting to send or receive. Okay. This is the period where I can send or receive anything to all the other nodes around me. And this active period or the duty cycle can be adjusted or can be configured based on certain requirements for quality of service. So if the quality of service requires specific limit on latency, or a specific limit on energy, or a specific limit on throughput, and so on and so forth, you can adjust your duty cycle according to that. Okay. So sensor MAC is generalized in the sense that it tries to set up some wake-up period and some active period, and in that case, the active period is fixed. So implicitly, this assumes that the traffic in my network is somewhat homogeneous, or it does not change a lot. Otherwise, you have to keep optimizing this duty cycle based on the traffic. Okay? But SMAC doesn't do that. FMAC does not perform any optimization with respect to the wake-up period and the active period. These are pre-configured parameters. So based on setting the active period or the wake-up period, you get certain performance. But this performance is not optimized for all types of traffic load. So for example, if the traffic load on the network is very, very low, many nodes will wake up, will stay active for some time, which is this time here, and it does not receive anything, but it has to keep itself awake. Okay? So in other words, certain active period assumes specific traffic pattern on the network. So it would be nice to have some information about the traffic on the network, so that we can change the wake-up period and change the active period accordingly. Okay. طبعا, since we're talking about contention-based protocol, first the beacon will during the active period, the beacon will synchronize. So when you receive a beacon and you decide to be part of this group, then you have to synchronize your active period and the wake-up period based on the synchronization signal that you get, right? Which tells you what is the duty cycle. So you have to synchronize yourself to that duty cycle, right? Other than that, during the active period, you use the normal Cmpe CA with RTS CTS. We know the RTS CTS. If any node wants to send to any node, then as long as we are in the active period, then any node in the group I want to send to, I have to send it RTS. When the node sends me back CTS, then I can send data and then acknowledge. Okay? This happens during the active period. Once the active period is expired, we go to sleep mode and we stay in the sleep mode until the wake-up period comes back again. Okay? So SMAC uses the MACA or the MAC control or the Cmpe CA with RTS CTS for the case of A to facilitate the ad hoc communication. And as we said before, RTS CTS resolves the head internal problem and the exposed terminal problems as part of the MAC layer. Okay? So any question in that case? TMAC or timeout MAC tries to resolve the issue of if we are in a very low traffic load, there is a very high chance that nodes, they go into an active period and they stay for potentially some period of time in active period and they are not receiving anything. Because SMAC, again, SMAC provides fixed active period and then a sleep mode. So what really SMAC facilitates is the synchronization between the nodes. And this synchronization, we can do it in a distributed way based on sending the beacons. Okay, so once the beacons are sent and I can receive the beacon, I can synchronize myself to this group, which means that we can sleep and wake up together. That's it. Okay, but there is a possibility that I can wake up and there's nothing to do. Okay, so TMAC tries to resolve this by having a variable active period. So the duty cycle here is not fixed, even within the same group. Right? So TMAC tends to have variable duty cycle or adaptive duty cycle, okay, based on the traffic load. And I can do that easily. Well, if a node like A is trying to send to node B, okay, using the normal Cmpe CA with RTS CTS, well, this is RTS. B will send CTS. So C, unfortunately, will receive CTS. So C will go into nav period, which means that it will stay idle, but it's active because it's receiving some signal, so it will stay active. However, D here is outside of the interference range of A and B, which means that D is an active period, right? But it did not receive anything. So in that case, D will count like a timeout, specific timeout. Once this timeout comes, it will prematurely go to sleep, even though it's in the active period, but it will prematurely go to sleep. And this is what will change the duty cycle. Because I stayed for a long time and I did not receive anything. There is no point of staying anymore. Of course, by adjusting this timeout, you can then address the issue of reducing the possibility that after you go prematurely to sleep, you are so unlucky that C tries to send you an RTS here. Like before the end of the active period, يعني C غلسة جدا سيدي. C waits until the very last part of the active period and then it wants to send you something. Okay? There is a possibility that this might happen. So you waited for this long time and you tried to save energy by prematurely going into sleep, but in that case you're unlucky. Well, the assumption here is that if I don't receive any traffic during this time, this means that the traffic load on the network is low at this point in time. Okay? So there is no point of waiting any further. But you're unlucky. You tried to go to a sleep mode, and C tries to. C did not adjust its own active period, by the way, right? Because here it receives CTS, so it's receiving something. So it knows that. So C knows that there is some traffic happening on the network. Okay. That's why C didn't go to sleep, because it says that even though I'm not part of this communication, C is not part of this communication, right? A wants to send to B, right? But C receives CTS. مش receives CTS. Over here CTS. Over here it's CTS. So it knows that it's not part of the communication. But for C, there is some traffic going on. So this is an indication for me that it's not wise to prematurely go to sleep, because there is some activity happening on the network. It's not wise for me to, even though I'm not part of this communication, but it's not wise for me because there is some traffic to go prematurely into sleep mode. D, on the other hand, does not do that, does not listen to anything. So in that case, it makes sense for D to assume that there is no traffic on the network.
For D, when goes for sleep, who will wake up?
Beacons.
When receive
All of them now, they know the beacon. They know the beacon, which means that they know the duty cycle, the current duty cycle. However, now, internally, I can decide to make my duty cycle adaptive based on the fact that I'm not receiving anything.
But when I'm receiving, I will wake up.
ازاي؟ ما احنا قلنا once we are in a sleep mode, we cannot detect the signals.
I can receive after I go for sleep. يعني
ازاي؟
ال RTS
No.
of C.
مين قال كده؟
ال RTS that C can come after timeout.
Right, but this one I missed.
Okay.
This one I missed. I cannot. ما هو this is this situation refers to C wants to send to D, but is hindered by transmission between A and B. يعني هو هنا يعني this point is interesting because C finds CTS, so CTS here tells C some interesting information. It tells C that you should not go to sleep mode prematurely because there is activity happening on the network. And you should not try to send to D at this point because somebody else is trying to send. And this whole thing contributed to the fact that D will not receive anything. And then it will time out prematurely to save energy and change its own duty cycle. C did not do that, and C will tries to send to D after D goes to sleep, in which case D will not receive the RTS and will not receive the data. Okay?
Yeah, Doctor, because if C sent anything, there will be interference and he will not receive anything.
If C, oh yes, of course, if C tries to send here,
Yeah.
then it will interfere with this transmission.
Right.
So it shouldn't do that. But luckily, C here is still part of the, indirectly part of the communication. So it knows what's going on. So it receives CTS, it can adjust its nav, network access vector, and it knows when this transmission is going to end so that it can try to send RTS to node D. But D is blind. I mean, D is completely blind for this. D is oblivious to all the activities that are currently happening. And it has to wait. And unfortunately, the timeout expires to conserve energy, and that was not a good decision in that case. So this is an example of a premature decision that happens by TMAC. And that's why if you were to simulate this on MATLAB, you will find that TMAC is significantly better from the energy consumption point of view compared to SMAC. because SMAC uses fixed active period, okay, regardless of the traffic load of the network. Okay, but T tries to adapt itself to the traffic of the network. If the traffic is low, I should conserve more energy. Should utilize that to conserve more energy by going into sleep prematurely. But you will also find out that the throughput for the case of SMAC will be slightly more than TMAC because of this situation, because of some situations like this. You decide to go to a sleep mode by expiring the timeout, but this decision was premature. It was not correct.
Just when you are saying that the active periods are synchronized using the beacons,
Right.
do you mean this period is the same for all, or it's
For all the groups that are synchronizing themselves to this beacon.
So it's the only period that anyone in this group can talk.
Right, right, right. And as we said, if you are like maybe there is a cluster here and there is a cluster here, they are forming themselves, and there is a node here on the border.
There is very high the chances of collision because
No, we're not eliminating collision. We're not claiming that we're eliminating collision at all.
all the nodes will wait until this more.
Yeah, but this was happening anyway. This was happening anyway, and it was happening more severely, صح? It was happening more severely. Even before we introduced SMAC and TMAC, it was happening, and it was happening more severely because in the case of 802.11 and ad hoc, you have hidden terminal problem, you have exposed terminal problem, based on which we tried to design RTS, CTS. So RTS, CTS seems to have reduced the collision a little bit, but it did not eliminate it. You can actually have collision in RTS, CTS themselves. So we're not claiming at all that we're eliminating collision. But this tries to address the compromise between, well, if the traffic demand is low, we might as well spend some time sleeping. This will actually reduce the collision. It will introduce latency, that's fine, مش مشكلة. I can live with that. Because the traffic demand on wireless sensor networks in general is relatively lower compared to 802.11. You are not expecting a small sensor to have the same data rates.
Yeah, but before the collision happens, if at least two try to send some messages during the sensing period or something like this, you know what will happen if any one of all the group
Right.
wants to send
Right.
in all the cycle.
In all?
In all the cycle from one beacon to another. If it wants to send from here to there,
No,
then
no, no. Who
it
said
will
that?
send
No, no, no,
into
no.
this
Only for
small
the
period.
duration.
All
No.
of them, all the one that want to transmit will transmit in all very small periods.
Oh, that's a good point. So, yeah, that's a good point. Because, yes, that's a good point. Because the active period is, so the active period is reduced because the duty cycle is high. Then we are reducing the time, but you are also reducing the number of people in the group. So you're doing that within subgroup. So you can adjust the duty cycle, or you can pre-configure the duty cycle to fit the subgroup that you have. So you are reducing the active period, okay, yes, which means that in this active period you are increasing the chances of doing collision. That's true. That's true in a way. But we're also reducing the number of people.
Maybe if collision increases, this means we have high traffic loads, so we can increase the traffic active period again.
Yes. So this will be an indication for us to increase the active periods. But we have some control mechanism now to increase it, and SMAC doesn't do that. SMAC doesn't do that. TMAC doesn't either, but it just uses this timeout to introduce some adaptive technique to the duty cycle. Okay, based on that, but it's not intelligent enough. It would be really nice to have clear idea about the traffic demand in this subgroup very accurately. In that case, I can adjust the active period and the duty cycle according to the traffic demand on this subgroup. Okay, neither SMAC nor TMAC does this. Okay, only TMAC implicitly does part of this when it tries to go into a sleep mode prematurely using the timeout. But even that is not optimized. Again, the key here is that since we do not have 100% accurate information and no ideal synchronization between the nodes, you always have to do this guessing, okay, based on heuristics. And this, based on how accurate this guessing is, you gain some somehow on the energy, and sometimes this comes with a little bit of cost on the latency. Okay.
I see that the problem of Bitcoin is that in subgroups, maybe one node cannot transmit. It will always mode sleeping. If it receives bacon, then in mode sleep. If wake up receives bacon, mode sleep. And it will never have the chance to transmit data.
No. You can transmit during the active period. In the active period, you can transmit or receive.
Active period, you will send bacon.
No. In the active period, you wake up based on the information that you receive in the beacon. The beacon tells you have an active period of, let's say, you have an active period of 3 milliseconds, and you have a wake-up period of 20 milliseconds, which means that you keep yourself awake for 3 milliseconds, and then you sleep 17 milliseconds before you have to wake up again. That's what the beacon tells you.
When wake up, then send?
When you wake up, then you have to ask yourself, do I need to receive something or send something? When you wake up, if you have data to send, you perform Cmpe, and then if you want to send, you send RTS, receive CTS. If you receive RTS from someone, this means that someone is interested to send you something, then you send CTS and perform the node. But everything happens during this active period. Okay. So during the active period, I can send or receive. If I want to send RTS. If there is something I want to receive or I need to receive, then I will receive RTS, which means I have to send CTS. So going back to this point, if you are on the border of two clusters, maybe you can decide to be part of the two clusters. Okay? In which case, you will adjust yourself based on two beacons. Some beacon tells you that this is the active period and this is the wake-up period. So this is one beacon and this is the other beacon. And the other beacon tells you that this is the beacon and this is the wake-up period. So this one tells you this is the wake-up period and the other one tells you this is the wake-up period. In which case, you have to be active here and you have to be active here. Which means that you're putting more load on your shoulder, okay, by being part of the two clusters. So you will consume more energy in that case by being part of two clusters at the same time. Okay. BMAC. So the issue that we tried to solve so far is that even though we're talking about contention-based, originally asynchronous type of protocol, right? Because contention-based nodes use Cmpe, right? Cmpe does not dictate any synchronization or any periodic transmission, right? Whenever you want to send, just sends. If there is nothing on the channel, send. But you don't have to restrict yourself to a specific time periods, right? Now, we're introducing the active period and beacons and wake-up period which enforces some synchronization, at least partial synchronization between the nodes in order to facilitate when to wake up and when to go to sleep. Right? But that's the only way for us to conserve energy. What else can we do? Okay? Can we conserve energy without doing any synchronization at all? Any synchronization between the nodes, which means that we do not have to send beacons and synchronize ourselves to the beacon? Can we do that? BMAC tries to solve this problem, or tries to advocate that, interestingly speaking, we can do something that does not restrict us to be synchronized in any way with the beacons. To conserve energy, yeah. Which is kind of interesting. But, of course, this comes with a cost. And the cost here is that we are transforming all the complexity and all the burden on the shoulder of the sender or the transmitter. Okay? The transmitter has to save the data for the receiver and then send, not a beacon in that case, they call it preamble. Preamble is just a way for us to announce that I want to send to that receiver, I want to send to you something. Okay? But who said that the receiver is synchronized to listen to it? So the only way for me to make sure that the receiver will actually listen to it is to make it very large. Is to make this preamble very large. How? So what happens is that this is the sender, and this is the receiver. What the receiver does in BMAC is that it wakes up periodically, but it doesn't have to synchronize itself to anything. It has complete independence. It wakes up like this to do sensing. Okay? When it wakes up, it senses the channel. If it senses something on the channel, then it knows that it needs to be awake for more time.
Random.
Periodic. لا السensing is periodic.
Fixed يعني in each
Yeah. But each one, I don't have to synchronize myself with anyone. It's only me. I don't need any synchronization with anyone, right? So I wake up, sense the channel. If there's something happening on the channel, then that's an indication for me to have to be awake for more time.
Happening in the channel, even it doesn't concern me.
Yes. Then, when I receive the channel, I will have to overhear what's happening. So we transform the complexity on the sender now. What the sender does is that if it wants to send to the receiver something, it has to send what we call preamble. This preamble, before it, of course, there is a period which we call it clear channel assessment, or CCA. Clear channel assessment. هو BMAC, what it does is that it finds that the contention itself sometimes has some false alarms because you do Cmpe, you do carrier sense multiple access, right? But the normal protocols like SMAC and TMAC and these protocols, or even 802.11, it uses some decision whether there is something on the channel or not, using just you listen on the channel. If the power is above certain threshold, then you assume that there is something on the channel. Otherwise, if it's below that threshold, you assume that there is nothing on the channel. Well, this decision might have certain accuracy, right? So the first thing that BMAC does is that because I'm not using any RTS and CTS here, I'm not using any RTS and CTS in the case of BMAC. It tries to compensate for this by having what we call a clear channel assessment. This is a more sophisticated technique for sensing, because the sensing part is very important. So BMAC tries to optimize or design very accurate sensing mechanism, okay, using some sophisticated filtering. So of course the signal on the channel might be like this, okay. So do you consider this activity on the channel, or there's maybe noise? So this is the issue now. So the normal protocols, what they do is that they strike a threshold like this. If it goes above that threshold, then there's something happening, even though this is a false alarm now. So the first thing that BMAC does is that it tries to use some filtering techniques, using very sophisticated, they use some moving averages, and they use some delays and median filtering and so on and so forth, to try to enhance the sensing part. So the accuracy of BMAC when it comes to sensing is more, but that's another story. So we sense. Now the sender wants to send to the receiver. Well, I don't have any synchronization when the receiver is going to be awake. So the only way for me is that if I find that the channel is idle, using the CCA period, clear channel assessment, I did assess the channel and I made sure that the channel is idle. So I send a preamble, and the only way for me to make sure that the receiver is going to somehow know that I'm trying to send to it is by increasing this preamble. I have no other choice. So this preamble is large enough to make sure that the duration of this preamble is more than the period that the receiver will wake up to sense the channel. So that here at this point, the receiver knows that I'm trying to send something on the channel. So it wakes up, and then it will start to receive the data. Here, I don't have to send RTS and CTS. BMAC does not do that. So for hidden terminal problem and exposed terminal problem, we try to send this preamble with a duration that's long enough to make sure that it reaches all the nodes participating in the transmission. The normal mode for BMAC, it does not use any RTS CTS. It can use RTS CTS, in which case we send a preamble, and then here we start sending RTS, and then we receive CTS from the receiver, and then we send data here, and then you can do the acknowledgement. Okay. But the key issue is here. The only way for us to eliminate the synchronization, yet make sure that we catch the time when the receiver is going to sense the channel, is by increasing the preamp. We have no way around it. Which means that we add more burden on the sender side. So what is the motivation here? So this is an overhead, clear overhead, right? Well, the idea here is that the problem really for wireless sensor networks is the listening side. Sending or transmission is less frequent in the case of wireless sensor networks, right? So the problem, if we talk about the problems that we have addressed, listening, right? Overhearing, all these are on the receiving side. صح? So we're trying to reduce this by just periodically sensing every now and then. Okay? So this way we sense for a short period of time and then we go to sleep. The transmission happens less often for the case of wireless sensor networks. Okay? So hopefully, this preamble overhead, because it's an overhead, right? Preamble is an overhead. It's a long duration, and we need to do it in such a way to catch the sensing part of the receiver. But hopefully this will not be done very frequently because of the fact that in wireless sensor networks that the transmission happens with less frequency. Using some experimentation, the BMAC outperforms SMAC and TMAC, especially when it comes to energy consumption, by a significant amount. Because of the fact that the complexity on the receiver is almost none. The receiver doesn't have to synchronize itself to anyone. It doesn't have to wake up on active periods. Only just wakes up. It doesn't have to synchronize itself with anyone. Just wakes up, sense for a very short time, go to sleep. Sense, go to sleep. That's it.
Self-management.
Self-management. I don't have to be part of a group or beacons, manage this. I don't have to do this. Only if I receive preamble from the sender, which will happen with a less frequency, hopefully, because the transmission is less frequent in wireless sensor networks. The complexity will be on the sender side, who will try to send a very long preamble. Of course, if the preamble is not long enough, it will not catch the sensing part of the receiver, in which case the sender will keep storing the data, right?
Yes.
And then later on it will send preamble again until it catches the receiver, because we don't have any synchronization between each other. You have a question?
Shouldn't the energy concern be bigger in the transmitter rather than the receiver?
Why? Yeah, it's of more concern in the transmitter, in the sense that the transmission is more expensive. The transmission is more expensive when you spend power on transmitting the actual data. It's expensive because of the fact that data is usually long and you spend power and so on. Yeah, so that's expensive. But transmission.
Transmitting energy, you use a lot of power to transmit compared with the power needed to receive, because you are transmitting.
For reception, you're not spending that much less power, by the way, because you have to activate all the decoding circuits. You have to activate all the decoding circuits. You have to receive the analog signal, convert it from RF to baseband. In the baseband, you have to convert it to digital. In the digital domain, you have to read the actual bits and bytes, and then extract the physical address, and then you ask yourself, is this physical address is yours? If the answer is yes, then you send the whole frame to the network layer and so on. So that's not much less expensive compared to transmission, as you might think. Okay, it's slightly less, but it's not that significantly less. Okay. So the only way for us again to break up this synchronization is using long preamble. This is the so to avoid this long preamble, we want to make sure that when we send the preamble, we meet two criteria. The first criteria is that there's no other way, which means that the channel for sure is idle. And I do that by using sophisticated techniques on clear channel assessment. If I do clear channel assessment properly from the physical layer point of view, which means that I need to sample the channel, I need to see all these samples, filter it, make sure that it's not noise, okay? Use some median filtering, moving average, all these combined techniques together. Well, the decision is that the channel for sure is idle. Then, okay, send a preamble with enough duration that guarantees that you will catch the sensing part of the receiver. Okay? So this way we don't have to have any synchronization. Okay? If we want, we can also add to it RTS, CTS, and data and acknowledgement, like SMAC and BMAC. In that case, we can compare with SMAC, BMAC. But it turns out that even without RTS, CTS, BMAC still performs better. Without use of the synchronization overhead. The synchronization overhead and sending beacons in some cases is problematic. Okay? We stop here or like? Okay, so the schedule-based part, we'll talk about it next time. We're going very, very slowly. I think this is this part of the lecture is maybe one of the hardest parts in the course. But luckily there are the papers. I actually explained maybe like 5 papers in this part. Yeah. 5 papers in addition to the information in the book. Okay, so this is actually, in a way, this is a state-of-the-art kind of research work, and we talked about the high-level idea in these 5 papers, in addition to the basic concepts that exist in the book. So when we are in the schedule-based, we want to divide the channel. We want to have a schedule between us, because if we are clustering ourselves into groups using the beacons and whatever method, then we might as well use the cluster head to divide the channel, and without having to use Sysma CA and Sysma CD. So divide the channel by using TDMA, using CDMA, using FDMA, using whatever. Okay, since we are naturally dividing ourselves into subgroups. So we'll talk about that next time.